Welcome to this video on exponential functions. Let's begin. The objectives of this video are to learn to distinguish an exponential function from other functions, learn how to graph an exponential function, and learn how to solve exponential functions using the equivalence property of exponential expressions. Let's first talk about the linear scale versus the exponential scale. When we first learn how to count, we learn about these numbers. And the pattern here is +1. To get from 0 to 1, we add 1. To get from 1 to 2, we add 1. To get from 2 to 3, we add 1, right? And this might seem kind of simple and maybe even like I'm insulting your intelligence, but that's what a linear scale does. If we want to move in the other direction, from, for example, 4 to 3, we would subtract 1. From 3 to 2, subtract 1. 2 to 1, subtract 1. 1 to 0, subtract 1, and so on and so forth. And that's how the linear scale works. It works, for negative numbers as well as positive numbers. When we move left, we subtract 1, and we move to the right, we add 1. So why am I going over this? Why am I telling you something that seems simple and basic and that you already know? Well, the reason is that human brains are uniquely wired for pattern recognition. So if you can recognize the +1, +1, +1 pattern of the linear scale, you can probably also learn to recognize the times or multiplication pattern in the exponential or logarithmic scale. It's usually called a logarithmic scale, but I thought that might be a little bit confusing because we're really not even learning about logs in this video at all, okay? So you can think of it as an exponential scale, and you'll see why in a minute. So what I'm going to do is instead of using these numbers, just as the values, what I'm going to do is I'm going to put a number down here. So this is going to be 2 to the 0 power. Remember, anything to the 0 power is equal to 1, right? Then this is going to be 2 to the first power. Well, 2 to the first power is 2. Let me move this one down a little bit so it doesn't take up so much room. Then we have 2 to the second power, which is 4. Then we have 2 to the third power, which is 8. 2 to the fourth power, which is 16. What if we go the other way? Well, 2 to the negative first power, remember, right? We know how to deal with negative exponents. We put them in the basement and then they're happy, right? So 2 to the negative first power is equal to 1/2. 2 to the negative second power is equal to 1/4. Then we have 1/8 and 1/16. So why am I calling this an exponential or logarithmic scale? Well, let's look at it. How do we get from 1 to the 2? Well, yeah, you could add 1, right? But when I go from 2 to 4, do I still add 1? Absolutely not, right? What do I have to do to get from 2 to 4? Well, the pattern is that I'm actually multiplying by 2. Multiplying by 2, multiplying by 2, okay? And the same would work here, right? 1 times 2 is 2. So as I move from left to right on this scale, the way I move from one number to the next is by multiplying by 2. Multiplying by 2. Multiplying by 2. That is the pattern, okay? So again, in a linear scale, the pattern is addition, right? As I move from left to right, I add. As I move from right to left, I subtract, okay? So let's see if we can figure out the pattern as we go the other way. What is the opposite or the inverse of multiplication? Well, it's division, isn't it? So 16 divided by 2, for example, would be 8, right? 8 divided by 2 would be 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. 1/2 divided by 2 is 1/4. 1/4 divided by 2 is 1/8. And 1/8 divided by 2 is 1/16. So that's how the exponential or logarithmic scale works. And if you can understand that, then you're really going to have a much stronger grasp on both exponential and logarithmic functions. So let's use the exponential or logarithmic scale to create a table of values and then actually graph an exponential function on the xy plane. Okay, so I'm going to keep this same exact base of 2. It's pretty simple and easy, right? So let's create the scale again. We just did it. So 2 to the 0 is 1. 2 to the first power is 2. 2 squared is 3. 2 to the third, 2 squared is 4. 2 squared is 4. 2 to the third power is 8. 2 to the fourth power is 16. 2 to the negative first power is 1/2. 2 to the negative second power is 1/4. 2 to the negative third power is 1/8. And 2 to the negative fourth power is 1/16. Now, if you look at this table, this is just a formatting thing, I didn't give us enough room to fit all of those values. So I'm just going to start at -3. And again, I'm going to omit -4 and +4 from this table literally just because I don't have room. Okay? So there's no other reason other than that. Okay? So let's fill this table in. So we have 2 to the -3rd power, right? 2 to the -3rd power is right here. What is 2 to the -3rd? Well, we just said it is 1/8. Right? Then we have 2 to the -2nd power. What is 2 to the -2nd power? Well, it's 1/4, isn't it? Okay, and we can keep going. We can keep pulling values off of our little exponential scale to fill in our table. Okay, and then once we've filled in our table, right, we're going to treat these as ordered pairs. So the first ordered pair that we have, my x value is -3 and my y value is +1/8. So where should that go on this graph? Well, remember, this is the x value, this is the y value. Here, this is the x value, this is the y value. So -3, we're at 1/8, so that's pretty low. Then we have -2, 1/4, that's still pretty low. Then we have -1, 1/2, and then we have 0, 1. We keep going. We're at 1, 2, then we have 2, 4, and then we have 3, and 1, 2, 3, 4, 5, 6, 7, 8. Okay? So we can have kind of a rough idea of what this graph should look like. I'm going to extend my y-axis a little bit up so you can see it. Okay? So I'm going to go over these dots just a little bit so you can see them better. So we have point here, 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 here. Okay? All right. So let's connect these dots and see what kind of shape emerges. Okay? So that's what my graph looks like. Okay? And what we're going to find is that this line here, this part of the graph, can get close to 0. Okay? And in math, we have a specific way of describing that. We say that it can get arbitrarily close. In other words, it can get as close as you want it to, okay? But it never actually reaches 0. Or if you want to be really all smart and stuff, you could say that it reaches 0 at infinity. Or, sorry, negative infinity, right? But of course, it's never going to reach negative infinity, so it never reaches 0. Okay, and if you want like a fun little thought experiment of like, why is that true, right? So the problem that you would have to solve is 2 to the what power is going to be less than 0. Okay, is there any finite number of x that would make that true, that would make 2 to the something power less than 0? So you can think about that, chew on that when you're bored. All right, so let's do another one. This time, we're going to make it interesting. We're going to change it up because guess what? Our base isn't a whole number anymore. It's a fraction, okay? So this is where it gets pretty interesting. So we have 1/2 to the 0 power. Well, remember, anything to the 0 power is 1. We have 1/2 to the first power. Oh, anything to the first power is just itself. Then we have 1/2 squared. What's 1/2 squared? Well, let's just think about it real quick, right? This is just 1 squared over 2 squared. Isn't that 1/4? Right? So this is 1/4. Okay. Well, what's 1/4? Sorry. Let's do, now we have 1/2 to the 3rd power, right? Well, that's 1 cubed over 2 cubed. Well, what is that? It's 1 over 8, right? And then this is 1 over 16. All right, so that's interesting, right? So now we can see that sort of getting smaller as our exponent gets larger. So right before we were getting, right, as our x value increased, right, as we moved from left to right on the number line, our values, our y values were increasing as well, weren't they? Now, right, with a base of 1/2, we can see that as our x values increase, what's happening to our y values? Aren't they getting smaller and smaller? So they're kind of doing the opposite. Okay, let's fill in the other part of the graph, or the number line rather. So we have 1/2 to the -1. Well, 1/2 to the -1, what is that? Well, isn't it just 1 over 1/2, which is actually just 2. So 1/2 to the negative first power is 2. What's 1/2 to the negative second power? You can literally just flip it, right? So you flip it and you square it. Okay, so when we flip it, it becomes this, then we square it. So 2 squared is 4 over 1 squared, so it's 4. We can continue this pattern. This is 8, and this is 16. Okay, so again, if you compare these, right, when we had a base of 2, we saw that as our x value decreased or approached negative infinity, our y value was getting smaller and smaller. It was approaching 0. Okay, but now, right, when I look at here, we can see that as our x value decreases, approaches negative infinity, we can see that our y value is increasing. And in math, we would say it's increasing without bound. In other words, it's not bounded. It can go on, get as large as you want. Okay? So again, just for the sake of space and fitting all this in, I'm not going to use negative or positive 4 for my exponents when I fill in my table. Okay, and again, there's absolutely nothing wrong with those ordered pairs. I just need to make this fit into the table. That's the only reason I'm doing that. Okay, so we have 1/2 to the negative third power. We already said that that was 8. So let's just pull these numbers and pull them in here. Okay, 1/2, 1/4, 1/8. Okay, so I have negative 3 and 8. So 1, 2, 3, 4, 5, 6, 7, 8. That's right here. Okay, then we have negative 2 and 4. So that's going to be right here. We have negative 1 and 2, 0 and 1, 1/2, 1/4, 1/8. Okay, so I have enough points now that I can kind of connect these points and try to sketch this graph. Okay, so again, I want to remind you that this is never going to touch 0. Okay, so we say it can get arbitrarily close. Okay, we say it can get arbitrarily close to 0. Okay, but it can never become negative. Okay, so again, let's compare these two problems. If we go back here, we can see that as we move from left to right, like this, our function is increasing. Okay, over here we can see as we move from left to right, our function is decreasing. Okay, so that's interesting. What is the difference between the two bases? Well, here we have a base of 2. So anytime you have a base that is larger than 1, 2 is larger than 1, you're going to have a function that is increasing. When you have a base that is between 0 and 1, like this, then you're going to have a function that is decreasing. Okay, so basically like a fraction or decimal, right? Something between 0 and 1. So keep that in mind, because those are some interesting and significant properties of exponential functions that we have to remember. So let's go over this. It says exponential functions have the form f of x equals b to the x, where b is larger than 0 and b is not equal to 1. So let's just think about why we need b to be positive, right? Let's just take 5 seconds and think about it. So let's pretend that my base was negative 2, right? So if I have negative 2 to the first power, that's negative 2. If I have negative 2 to the second power, that's positive 4. So I don't know if you can tell, but you're going to get this really, really weird oscillation behavior where it goes back and forth between negative and positive. It jumps basically on either side of the x-axis, the y-axis. Okay, so we don't normally graph something like that because, again, the appearance of that graph would be quite strange. So that's why we need it to be positive, so it doesn't oscillate between negative and positive numbers. Why don't we want it to be 1? Let's think about that. Well, let's suppose it was 1, right? So we have f of x equals 1 to the x power. Well, 1 to the first power is 1. 1 to the second power is 1. 1 to the fifth power is 1, right? That's not an exponential function. That's just the line y equals 1. So when you let b equal 1, you just have a very boring, simple linear function. You just have a horizontal line, okay? So that's why b can't be 1. Okay, so then the domain. Remember, the domain is the set of all allowed x values. So x can be anything you want. You can see it says all real numbers, or when we write it in interval notation, it's negative to positive infinity. Okay. The range, however, and I alluded to this in my previous graphs, right, when we were talking about this, I said that it can't drop below 0. It also can't equal 0. So again, another fun little mental exercise. What value of x is there? Does there exist a finite value of x, real value, that would make 2 to the x power be equal to 0? Okay. The answer is that it doesn't, but you can play around with it, try to make it work, and you'll find out that it doesn't. Okay. So again, I already mentioned that if your your base, is between 0 and 1 exclusive, okay, then our graph is decreasing. You can see that in the left picture right here. Okay. If b is larger than 1, I'm basically multiplying by a number bigger than 1 over and over and over again, right? So our graph is going to be increasing. And you can see that here in the specific example of f of x equals 2 to the x power. So one thing that's really important to remember when we're learning about exponential functions is that we don't confuse them with functions that we've already learned about in the past. For example, f of x equals x squared. So let's compare f of x equals x squared to f of x equals 2 to the x. So what is the difference between these two? Well, notice that here my base is x, right? And my exponent is 2. Basically, it's a constant. Okay? If I come over here, my base is constant, isn't it? I think I just spelled that wrong. Constant. Okay? But my exponent is variable, right? So they're kind of the opposite of each other, right? Here I have a variable raised to a constant. Here I have a constant raised to a variable. Do you see that? Okay. And you can look down here. You can look at the table of values and how the graphs behave, what they look like. And you can see that they look very different, right? If I look at this x squared, this quadratic function, of course I get a parabola, right? It has a lot of different properties. It is symmetrical around the line x equals 0, first of all, right? You have some symmetry there. And then if I look over here of f of x equals 2 to the x, there's not really any symmetry that I can see here. Okay, so let's think about the domain and range of these two functions. So if I look at my parabola, remember my domain, we learned this a while ago. Domain is all real numbers. Okay, remember the two reasons we have to restrict the domains of functions is 1, if we try to divide by 0, or 2, if we try to take the even root of a negative number. And obviously neither of those are happening. But if we come over here to 2 to the x, we're also not trying to take an even root of a negative number, and we're also not trying to divide by any variables, right? So my domain over here is the same thing. Okay, what about our range? Well, you can see that this function starts at 0, so it is 0 to infinity, right? But guess what? When x is 0, y is also equal to 0, isn't it? So 0 is part of my range here, okay? And of course, quadratic functions, this parabola could occur anywhere in space, and so your range, it could shift around, okay? But here, remember, we have, this is something you'll learn about more if you take pre-calculus 1, we have what's called a horizontal asymptote, okay? So I cannot include 0 in my range, okay? Again, my function can get arbitrarily close to 0, but it's never going to get or reach exactly 0. So the next thing we need to learn is the equivalence property of exponential expressions. Some exponential functions can be solved using the equivalence property of exponential expressions. Let b, x, and y be real numbers with b greater than 0 and b not equal to 1. Then b to the x equals b to the y becomes x equals y. So what does that mean? Well, let's look at this expression below. Basically what they're saying is, since the bases are the same, and we're told that both the entire expressions are the same, then it follows that in order for these two expressions to be equivalent, the only way that can be true is if the two exponents, the exponent of this guy is equal to the exponent of that guy. That's all that we're saying, right? Because 5 equals 5, so therefore this guy must equal that guy. That's what we're saying. Okay, so this is pretty cool, right? Because now we have this nice little linear equation that's pretty easy to solve. So we have 3x equals 3 divided by 3 divided by 3. We get x equals 1. So we're done, right? And if you're like, I don't believe you, lady, what are you talking about? We could just put 1 back into our equation, couldn't we? And we can prove to ourselves that this is true. So 3 times 1 is 3. So we have 5 to the 3 minus 1 is equal to 5 squared. So we have 5 squared is equal to 5 squared. So lo and behold, it really, really, really does work. Okay? All right, let's do one more like this. Again, we can see that the bases are the same. Both of them are 2's, right? And the whole expressions are the same because we're being told that they're the same as each other. They're equal to each other. So then we must say that we just logically reason that the only way for this statement to be true is if the exponents then are identical. So again, we have a simple linear equation, 5 equals x minus 3. So we add 3, and we get 8 equals x. So let's look at some examples where the problem is written in a way that requires an additional step. So if I look at this equation, you can see I have a 5 on the left side. I don't have a 5 on the right side, do I? Okay, so I don't have the same exact basis. But what I can do is I can use this exponential scale to figure out where 125 lies. Is it a power of 5, right? As soon as I see the 5, I know that my base is going to be 5. So let's fill out the scale. Well, 5 to the 0 is 1. 5 to the first power is 5. 5 squared is 25. 5 to the third power is 125. So what I can do is I can rewrite this as 5 raised to the 3x minus 1 power equals 5 to the third. Now let me ask you this question. How did I know that I should go right and not left on this number line? Well, remember when you have a base that's larger than 1, right, as you move right on the number line, your values are going to get larger and larger. Well, 125 is larger than 5, isn't it? So I need to raise it to a positive exponent. Okay, so now that I have an expression where both of my bases are the same, I can now apply that property that we learned about. So we have 3x minus 1 equals 3. So we add 1 to both sides. We get 3x is equal to 4. I'm out of room. Bring it over here. So divide both sides by 3. We get x is equal to 4/3. Okay, and again, you could always put that 4/3 back in there and prove to yourself that this is true. All right, let's do another example. So we have 1/4 and we have 8. Okay, what base suggests itself to you? Can you think about it? Pause the video, write down your number. I'll give you a hint, it's not 4 or 8. What base is appropriate for this problem? Okay, the answer is the base of 2, and I'll show you why. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8, right? So now we have one of the values that we need. Going the other way, we have 2 to the negative first power is 1/2, and then we have 2 to the negative second power is 1/4. So that's the other value that we need, okay? So I'm going to rewrite 1/4 as 2 to the negative second power, and then I'm going to rewrite 8 as 2 to the third power. Okay, so now we have to use that power rule. When I have a power raised to another power, what do I do with those two numbers? Well, what we do is we multiply them. So I have 2 to the negative second power is equal to 2 to the 3 times x, or the 3x power. Now that I've obtained the same base, what do I have to do? Well, I have to set my exponents equal to each other, and I have a one-step linear equation that I can solve. I get x is equal to negative 2/3. All right, same thing. We have 8 and we have 4. Again, what base do we need to be looking at? Well, once again, we need to look at a base of 2. Remember, 2 to the 0 power is 1. This is 2. This is 4. This is 8. Okay, so I'm going to rewrite 8 as 2 to the third power. Okay, and it's still being raised to the x plus 3 power. Okay, I'm going to rewrite 4 as 2 squared raised to the 5 minus 2x power. Notice that what I'm doing is I'm putting both of those exponents in parentheses to remind me that when I multiply my exponents, this is going to give me 2 to the 3x plus 9 power is equal to 2 to the 10 minus 4x. Okay, so if I lost you there, if you're like, whoa, lady, where did that come from? Let me show you. What I'm doing is 3 parentheses x plus 3. So I have 3 times x is 3x, and then I have 3 times 3, which is 9. Over here, same thing. I have 2 times the quantity of 5 minus 2x. 2 times 5 is 10. 2 times negative 2 is negative 4x. Okay, so that's where that came from. Be careful. Make sure you multiply everything out. Okay, so now, right, I do have the same base. So now that I have the same base, I can just set those equal to each other, and I'll just have a multi-step linear equation that I can solve. Okay, so we have 3x plus 9 equals 10 minus 4x. I'm going to add 4x to both sides. I get 7x plus 9 equals 10. I subtract 9 from both sides. I get 7x is equal to 1. Divide by 7, divide by 7. Let's do that over here. Sorry about that. Did not plan well space-wise for this problem. So I have x is equal to 1 over 7. That's pretty crazy, right? Even if I were to put it back in here, I'd probably have to use a calculator to evaluate both sides. Okay, so you can see the value and the merit of this approach. All right, let's do one more example. This time I have a 1/9 and I have a 3. Can you figure out what base, what scale are we using? Well, let's try 3. 3, 3, 3, 3, 3. So 3 to the 0 power is 1, 3 to the first power is 3. So we've got one value, right? How am I going to get a fraction? Well, we need to move to the left. So 3 to the negative first power is 1/3. 3 to the negative second power is 1/9. Okay, so I'm going to rewrite 1/9 as 3 to the negative second power, and I'm raising it to the 2x power. Okay, 3 is fine, right? He can stay just as 3. So I have 3 to the 7x minus 1. Okay, remember what we need to do is we need to multiply these two numbers. So negative 2 times 2x is negative 4x. So I have 3 to the negative 4x is equal to 3 to the 7x minus 1. So I have negative 4x equals 7x minus 1. Going to subtract 7x from both sides. It gives me negative 11x equals negative 1. I'm going to divide both sides by negative 11. So I get x is equal to positive 1 over 11.